Right, this is 7.5.1. Force due to magnetism. Now, magnetic fields are called B fields, which might not make sense because students would think magnetic starts with an M, it should be called M fields, but no, they're called B fields. So, gravitational fields, G fields, electric fields, E fields, and magnetic fields, B fields. So I want you to learn that and remember that. So these are B fields, and in electric fields, the field lines point from positive to negative, and in B fields, the lines point from north to south. So that's for magnetic. Now, at A level, you need to do magnetic fields work in 3 dimensions. So the first 4 directions are quite simple to understand, but that introduces 2 new directions that you have to be familiar with. So, our B field directions are up, down, left, right. So that's 2 dimensions so far. Each dimension gives you opposite directions, up and down, for example, 1 dimension, left and right is another dimension. And then the 3rd dimension is going to come out of the paper or into the paper. So coming out of the paper is like an arrow coming towards you. So if an arrow is flying towards your face, you're going to see the point of the arrow. So out of the paper are points. Sometimes we can call this out of the plane of the paper. Now sometimes points are difficult to see, so they're reinforced by a circle on the outside of the point, just to make it easier to see. And then into the paper, it's like an arrow's flying away from you. In other words, you've shot an arrow, so you see the feathers on the back of the arrow when the arrow's flying away from you into the paper. So that's represented as a cross, which is into the paper. So typically when we talk about magnetic fields, we're going to look at uniform fields or regions that are uniform fields, so small regions. So we'll do 2 examples of what these fields will look like, which are going to be the new versions of fields that you haven't seen before. So for magnetic fields, we'll do 2 uniform fields. So here's one, which is an into the paper field. So here we've got field lines are into the paper. And we'll do another one on this side. And here we've got field lines are out of the paper. Now both of these are examples of uniform fields. You can tell they're uniform because the field lines are equidistant apart. So the density of the field lines remains constant. So these are both uniform fields because field lines are equidistant, which means constant density. Now this is going to start to make a lot more sense as we get into the equations for magnetic fields. But each of these field lines are called flux. So the field lines are called flux. So let's do a simple example of a force on a wire in a magnetic field. Force on a current carrying wire in B field. It's quite a long subheading, but there you go. So we'll do a uniform field once again. So this is our B field. We'll give it some flux density called B. Now flux density is like the field strength. In fact, it is field strength. So we call it the magnetic flux density. How dense these field lines are. The more dense they are, the stronger the field is. And in that field, we place a wire. So this is a wire. And the wire carries a current, I, towards the right. The length of the wire in the field is equal to L. Now we don't care about the total length of the wire because it could be an extremely long wire. We only care about what length of that wire lies within that field. So if that field were to end in this drawing, then any length that's outside of that field is irrelevant. Now, there is an angle between the current and the magnetic field lines. So at the moment, if you were to look at the current, it goes towards the right, and the magnetic field lines point into the paper, so they're at right angles to each other. We could position this wire so that it goes at some angle going into the paper or some angle out of the paper. That would give us an angle between the magnetic field lines and the wire. And if we did that, then the force that this wire will experience will change depending on that angle. Yeah? So here let's add on wire at 90 degrees to B field. So the equation that describes a force on this is F equals to Bill sine theta. Put a box around that. If theta equals to 90 degrees, then F is max. And if theta equals to 0 degrees, then F is 0. And then we'll define all of these terms. So F is the force measured in newtons. B is the magnetic flux density. And the units for that are the Tesla. I is the current measured in amps. L is length measured in meters. And theta is the angle between the field and current slash wire.
So if the wire is going in the same direction as the arrow, it goes one into this, there'll be no force.
Yeah, so if the wire was in the same direction as the field, yeah, then there will be no force. So for example, if I drew another how do we change colour? Right, it's not coming up. Sort it out there. If we drew another wire here, for example, let's say it was coming out of the field like this. So wire at 0 degrees to field lines. Then F of this one will be 0. And F of this wire is equal to BIL, because sine 90 is 1. Yeah? Okay, now, part of this, you're going to have to determine which direction the force is going to be. Direction of force. So for this we use Fleming's left-hand rule, which is also called the motor effect. So you need to hold your thumb pointing upwards. Then you need to have your index finger pointing straight. And then you make your middle finger point at 90 degrees. So if you're holding your hand in front of you, like you're pointing a weapon at someone, that will point towards your right. And then you keep all three of these at 90 degrees to each other. And you're going to use these to work out which direction certain things are. So you might be given 2 of them and asked to work out a third one. So the easiest way to remember it is to remember it as FBI. So I like to start from your thumb and work your way down. So you see how your thumb is the highest thing, then it goes down like steps, right? So you're walking down the steps, you do FBI. So your thumb is the force, your index finger is the magnetic field lines, and your middle finger is the current. FBI. So thumb is force, index finger is field lines or magnetic flux, and your middle finger is current. Put a box around that. Now, let's think of a situation. What happens if the current and the magnetic field lines are parallel? Well, our B and our I fingers don't point parallel to each other, so therefore there's no force, because it cannot be done with Fleming's left-hand rule. Yeah? So if 2 of these things are parallel to each other, then there is no force. It cannot be done with Fleming's left-hand rule. So F, B, and I must be at 90 degrees to each other. So force is not only 90 degrees to the field lines, it's also 90 degrees to the current. Likewise, the field lines are at 90 degrees to the force and the current is 90 degrees to both of them as well. So add a little note here. If I and B are parallel, then there is no force. Let's do a quick example. So which direction is the force? So we'll put the end of two magnets here. So this is a north, this is a south, and then we'll do a wire going into the paper with current I. So in this case we do Fleming's left-hand rule, where B is going to point towards the right, and then I, we have to rotate our hand so that we maintain B going towards the right, but I has to point into the paper, so we just simply rotate our hand, and we can see that our thumb then points down. So the force is down. We'll do another one, so we'll put the south pole over there, we'll put a north pole down here, we'll put the current flowing to the right. So we do the same thing again, Fleming's left-hand rule. This time we have to make our index finger point upwards, and then we simply have to rotate our hand or our body so that the current points towards the right while maintaining the flux pointing upwards. So we can see that the force comes out of the paper. So here we've got force is out of the paper. We'll do another example. So put our north pole and our south pole, and we'll put our current carrying wire. Oh, but now they're parallel to each other, so there is no force here. And then finally, we'll do north pole, south pole, and we'll do our current coming out of the paper. So again, using Fleming's left-hand rule, we have to point our index finger to the right, and then our middle finger should be pointing out of the paper, and so we get a force going upwards. Now, we'll do a slightly more complicated one, which is how motors turn. So try and do this one in 3 dimensions. So if we had a north and a south pole, and in between the two we put a loop of wire, and current flowing through the wire was as such. Now we can see that there are 3 sections to this loop that we're interested in that can potentially carry some force. So I'm going to label these sections as A, B, and C. Now, section B is parallel to the field lines. So section B of this coil of wire has no force on it. So B is parallel to field lines. So B contributes 0 force. Now we have to look at what A and C do. So if we look at A and C, we're going to have our index finger pointing from north pole to south pole. Then we have to rotate our hand so that A kind of looks like it's pointing into the paper. So if we did that, we can see that the force at A is down. Then we do the same thing at C, and we can see that the force at C is up. So on the right-hand side, I'm just going to sketch that just with the coil of wire, and we can see what happens. So force on coil looks like so at A, we said that it goes down. So we've got force going down. And at C, we said that the force goes up. Two forces on opposite sides acting in opposite directions. Well, this is a couple. Forces are a couple. So when you think back to moments, this is going to cause a coil to rotate in which direction?
Left.
It's not left. That's not a left is not a rotation. Rotation is two directions.
Anti-clockwise.
Anti-clockwise. So the coil rotates anti-clockwise. Now, let's do a common example that comes up in exams. I'm trying my best to sketch this. It's quite a difficult one to sketch. Didn't come out how I wanted it to. So we have a magnet assembly sitting on a balance with a current carrying wire, and this reads 327 grams. We'll label this as south and north. So the magnetic flux density is equal to 0.3 Tesla. The current going through the wire is 2.0 amps. And the length of the wire is 8.0 centimeters. So the questions are A, the direction of the force on the wire and on the magnet assembly. And B, what would the reading be if the current was turned off? You can pause the video here to attempt this question and then press play once you want to see the answers. Okay, so for the first one, first we want to find the direction of force on the wire. So here we're going to use Fleming's left-hand rule. So we need our index finger to point from north to south. Now in this situation, you might find it hard to point your hand in this direction. So the trick is, move your body to face the other way. So if you turn your body to face another direction, you might find it a little bit easier. So if you stretch your arm out towards your left rather than towards your right, your left arm that is, it'll be much easier to point the field in the right direction. So we can see here that the wire experiences a force upwards. So A, wire experiences force upwards. Now, the magnetic assembly will experience a force downwards because this is a Newton-free pair, so it's equal and opposite reaction. So magnet assembly experiences force downwards because it's a Newton-free pair. Now, part B. We know that the reading that's on the balance is due to two things. Number one, there's the weight of the magnet assembly, but there's also an extra force being applied downwards due to that magnetic field interacting with the current that's going through the wire. So let's put it in terms of forces. The force on the balance is equal to the weight of the magnet plus the force due to the magnetic field. Now let's write these out in terms of numbers. 327 grams times by G is the force that's being experienced by the balance in total. So here we put 0.327 G is equal to the weight of the magnet. Well, we don't know what the weight of the magnet is. We don't know the mass of the magnet. But we know there's going to be mg plus the force due to the magnetic field. Well, F equals to Bil, B-I-L. So we just replace that with B-I-L. And now we can start to see how we're going to work out the mass that would have been read by the balance had we switched that current off, which is just going to be the mass that was read times by G minus that extra force that was introduced by that current being turned on. Then we can divide the whole thing by G. So let's just rearrange this. So we've got 0.327 G minus BIL, all divided by G, is equal to the mass of the magnet assembly. And now we just put our values in. So M equals to 0.327 times by 9.8 minus 0.3 times by 2 times by 8 centimeters, so 8 times 10 to the minus 2, all divided by 9.8. If you could just put that into your calculators and give me a value. 0.322 kilograms. Now we do a quick sanity check. Is it reading less than it did before?
Yeah.
Yes, it is. So now we know we've done it correct because we've removed the excess force that was caused by that magnetic force due to that wire. So the balance was reading in grams though, so now we convert this back to grams. That's 322 grams. Right, moving along. This is going to be the last part of this lesson, and this is the magnetic field definitions. So we start with magnetic flux density. So this is the force acting per unit length of wire carrying 1 amp of current. Put a box around that. So the Tesla is equal to a Newton per meter per amp. So we can then say that 1 Tesla is a magnetic field which produces a force of 1 Newton on a 1 meter of wire carrying 1 amp of charge. I'll put a box around that. And that's the end of 7.5.1.